Okay. So we've got one more session tonight, and then we'll be done. I'll have all your assignments ready by tomorrow, and I'll send them back to you. And I think there were four of them. Whatever the number was, that'll be your grade, and I'm sure you'll do just fine. So in the meantime, we just have that one last topic to wrap it up. And now, of course, we covered a lot of material this semester, but there's so much more. If you're really interested in this area, I don't really know what other courses they offer in this area that you might be able to take that are more specialized. But this gave us all a very solid background, I think, in this area because we've covered the four basic types of derivatives, forwards, futures, swaps, and options. We've seen how to price them, and we've seen how to or how we've understood how they work. And we've understood some very important hedging strategies. What we're going to do tonight is take a look at an applied area where a lot of use is made of derivative securities. And that area is called risk management. And as the name suggests, in risk management, the goal is to, of course, manage risk. And one of the best ways to do that is with the careful use of derivative securities. So the two fields are very closely related to each other. The value risk methodology that we'll be looking at tonight was designed to make it possible to measure risk in a fairly straightforward way, and then help us understand how we can use derivatives to help us reduce our risk to levels that are we may be comfortable with. And it also can be used to help banks determine, let's say, how much their traders are allowed to trade with. And it can be used to help understand the performance of portfolio managers. So it's a very important and interesting area of study. It's a little bit more statistical oriented than some of the other topics we've looked at. But really, the bottom line is that if you understand the normal distribution, that's all you really need to understand what we're about to do. The rest comes from our understanding of derivative securities. And so let's take a look. Let's see, where are we? Yes, here we go. So we have some Excel examples as always. This is especially useful in a topic like this where we have statistics involved. Let's see, how many examples do we have? All right, well, here's an interesting one. This one, you can see we have stock prices, and we're going to use those to derive some interesting results. And we also have a brief detour into statistics where we look at the normal distribution. And we also have available to us, a slight variation of what we're doing tonight is called expected shortfall, and we'll be looking at that as well. All right, so let's get to the slides. And we'll introduce value risk, which is a model that's used in the risk management field to help measure risk. Okay, it's a statistical measure. It's very heavily based on modern portfolio theory. And basically, a point of this whole model is to show us the magnitude of losses that could potentially occur during a given time horizon. And we also apply to it a specific, what we call level of confidence, so that we have some sense of what's likely to happen. And so knowing that we don't, of course, know exactly what will happen, we can specify a level of confidence and then give ourselves an estimate of how much we might potentially lose over a given time frame. Now, this can be done in terms of dollars or percentages, as the case may be. So let me show you a very simple example. Suppose that a pension fund holds $100 million worth of IBM stock. Based on some methodology that they've used, they've determined let's say this pension fund has some quants working in the back office there, and they've used their statistical methods to determine that every 20 trading days, or 5% of the time, the portfolio can be expected to lose more than $20 million. Okay, now that's based on a lot of factors, such as the volatility of the stock, but let's just say that this is what they've come up with. Now, what that also implies, though, is that 19 out of every 20 trading days, the portfolio should lose either less than $20 million or it should actually make money. Now, since we're studying risk management, we're not terribly concerned at the moment with profits. We're just trying to identify the potential for losses, because that's really what hedging is all about, trying to determine how much you could potentially lose, and then finding strategies for keeping that as low as possible. It's kind of like with insurance. What's the purpose of insurance? To protect you from disastrous outcomes. So here, what we're attempting to do is identify what kind of disastrous outcomes we're potentially exposed to, along with some idea of how likely this is to happen, so that we can do a good job of determining how much hedging we need to do. Now, of course, we can't just go out and buy insurance policies on our stocks and bonds, but we can do something equivalent to that by buying derivative securities. So we have to understand how much risk we're facing before we go ahead and start up a hedging program. The problem with hedging is that it can be very expensive, so we have to be very careful with it. We obviously don't want to leave ourselves exposed to enormous quantities of risk, but we also don't want to spend all of our money on insurance either. I mean, it's like there's got to be a happy medium between the two. So the value risk methodology makes it easier to do this than other equivalent approaches, which, by the way, I just want to mention before we get any further into this, the value risk methodology hasn't really been around for all that long. It was developed at JP Morgan in the early mid 90s. And, at the time, the model was really meant for the benefit of the clients of JP Morgan. In other words, a lot of their clients would call up and ask for a discussion about how much risk their portfolios had in them. And Morgan realized pretty quickly that at the time, it was a very difficult thing to do because most portfolios contain a diversity of assets. In other words, they might not have been all stocks or all bonds. And with the technology that existed at the time, risk measures were available, but they could not necessarily be combined with each other. So that if I had, for example, a portfolio of both stocks and bonds, it wasn't really realistic that I could come up with a number that tells me how much risk is there in my portfolio. I would have had separate risk measures for the stocks and separate risk measures for the bonds, but it would have been difficult or impossible to combine them into a single number that reflected the entire portfolio. So that's really why this was invented. And another motivation for inventing value at risk was that in a lot of cases, the financial managers in this, JP Morgan found that they had to explain what they were doing to the senior level executives who are not necessarily involved in finance. And so there needed to be a way to communicate this information to the senior executives in a way that wasn't too overwhelmingly technical, something that you could explain to somebody in English. And that was part of the problem. Imagine the CEO of the company has a background in marketing and he doesn't really know anything about, let's say, derivative securities. You still have to be in a position to explain to him what kind of risk management strategies you're implementing without overwhelming him with all the technical details. So that was another motivation for creating this product. Now, at the time, I don't believe they understood exactly how important this would prove to be, because they stripped it off and sold this model, and the people who were working on it, they basically created a separate division and then sold it off. And it was an independent company for quite a while. It was called RiskMetrics. And so the RiskMetrics company continued to implement the value at risk methodology for clients. They also published a lot of important research. And eventually they were bought out by Morgan Stanley. And as far as I know, they're still part of Morgan Stanley. But JP Morgan invented it. But it's like a lot of developments like the Black-Scholes model. And initially, nobody was really, or it wasn't that obvious how important this would turn out to be, because everybody uses it now. Just like Black-Scholes, there are a lot of flaws in the assumptions in value at risk, but yet it's useful enough that everybody on Wall Street continues to use it. Now, another issue with value at risk, besides the assumptions, and we'll discuss this later on, is that the full-blown value risk methodology is potentially at least very, very time-consuming to implement. So much so that a lot of research is dedicated towards finding ways of streamlining our calculations. And a lot of the research has been done and methods have been found for speeding this up. But unfortunately, a lot of these alternative methods involve much shakier assumptions. And it's not always clear that these new methods are actually any better off than what's being done in the original value risk modeling. So anyway, so the value risk has a very interesting history, and it's still, still being used 25 years later. It's still widely used. So in spite of all of its problems, it turned out to be a very useful framework because again, it suddenly becomes possible with value at risk to combine all the risks in a portfolio into a single number. Okay, and that's really the whole point of it. We can point to a portfolio and no matter what's in it, we can say there's X dollars worth of risk in this portfolio. And that's a very important thing to be able to do. Anyway, so let's get back to the statistics. So we've been told that with this IBM stock, once every 20 days, it potentially could lose more than $20 million or 20% of the portfolio value. So because we express this in terms of 5% of the time, we can say that our results here are calculated with a 95% level of confidence. The number that we come up with can be called 5% VAR. And if you notice too, when you calculate VAR, it has to be in terms of a single time frame. In other words, this is every 20 trading days. So the VAR that we're calculating here is referred to as daily VAR because it refers to how much the portfolio value can fluctuate over a single trading day. Now, let's take a little detour here. What exactly is happening? Imagine you've got a lot of data about this stock, and you know from experience what's likely to happen with the returns to IBM stock. So let me just draw up a quick little diagram here. And so we can create what's called a histogram, which basically represents the returns to IBM stock. And each bar represents a different rate of return. And the heights of these bars represent frequencies. So for example, let's say this bar represents breaking even. And remember, these are daily returns. And then we have other bars that represent different rates of return. For example, this is 1% gain. This is a 2% gain, 3% gain. This is a 4% gain. This is a loss of 1%. This is a loss of 2%. And then finally down here, we have a loss of 3%. So it's hard to tell by the way I've drawn it, but let's just say this represents 5% of our outcomes. Okay, so that shaded region could be thought of as the left tail or left 5% tail of a probability distribution. So what that actually means is that with 95% confidence, or actually what I should say, yes, 95% confidence, or we can alternatively say that 5% of the time, our losses can reach or exceed 3%. Okay, so if the portfolio is worth $1 million, 3% of that would be $30,000. And so let's say that would indicate that our value at risk is $30,000 over the coming trading day with a confidence level of 95%. In other words, we're 95% confident that over the coming trading day, we could potentially lose 3%, but only once out of every 20 trading days. The rest of the time, we'll either lose less money or else we'll make money. So this is the number that we're focused on. Right down here, what could potentially go wrong? Although it's a very small percentage of the time, it could be enough that we have to worry about our position. We may decide that it's time to do something about our risk. Like, I mean, 3% doesn't sound like a lot, but what if that minus 3% was really, let's say instead it was minus 10% or minus 20%? That might catch somebody's attention and say, listen, we can't allow ourselves to take this kind of risk. Even if we only lose this much money once out of every 20 trading days, that still might be too much. Suppose, for example, this is a pension fund. And pension funds have to take it easy with their money. They cannot be risking it because otherwise people will retire and they won't have any money. So for a very conservative organization, this might still be too much risk. They may think, maybe we should do something about this. Or for a very aggressive hedge fund, this might actually be too little risk. They may decide that they're not taking on enough risk and maybe they should do something about that. But the value risk methodology is all it's designed to do is tell us how much is potentially at risk at a given level of confidence over a specific time frame, like in this case, every day. It's up to the portfolio managers to decide whether this is acceptable or not. Okay, and the risk managers. So now if we have enough data though, you might see, if you've seen this before, if I take my histogram, and if you look at it very carefully, the way the bars are laid out, the bars, even though I define them as frequencies before, they can still also be thought of as probabilities. If I have enough of these bars, if I have enough data, then something interesting starts to happen. If you've seen this before, the distribution starts to resemble what we will call the normal distribution. Okay, so in other words, the returns closely resemble the normal distribution. Now, I'm sure you've heard of the normal distribution. You might have started to figure out how it works, but the important detail here is that the normal distribution resembles a bell-shaped curve, and it has a lot of other useful properties that we often assume that returns to stocks have. As a matter of fact, you know what I've done for you here? I've put together a spreadsheet where we can quickly review the normal distribution, just in case it's been a long time. So that's what this one is all about, the normal distribution example. It's basically a quick review of how the normal distribution works and how we can implement it in Excel. Okay, so first things first, imagine the following situation. So we have the mean or average return to a portfolio of stocks that's 10%. Now we're talking about so much per year. We know that the returns will not equal 10% every year. There's always a lot of uncertainty associated with these returns. How do we measure that uncertainty? We use something called the standard deviation, which we've seen before, to represent the risk, or sometimes it's called volatility, of financial assets. Now, the normal distribution is often used to represent the returns to financial assets, in particular stocks. It has a lot of helpful properties that, in practice, while the returns may not be exactly normal, they're awfully close in many ways. So imagine the scenario here where we have portfolio A. It has a mean return of 10% and a standard deviation of 2%. So you can see the way I've drawn it, 10% is the mean of this distribution. And we use the Greek letter mu to represent the mean of a probability distribution. The standard deviation is represented by the Greek letter sigma. And so based on the shape, you can see that a large percentage of the returns are somewhere between 8 and 12%, which can be interpreted to mean somewhere between one standard deviation above and below the mean. In fact, statistically, this represents about 2/3 of the normal distribution, let's say 68%. So if you owned a portfolio of stocks, this portfolio of stocks, and it has these properties, that means the chances of your return falling between 8 and 12% is approximately 68%. And of course, as you move further and further away from the mean, the probability of being significantly off from the mean is quite low. Okay, so in other words, the bell-shaped curve has this special shape. It has a lot of area in the center, and it has a lot less area out here in the so-called tails. They're actually called tails, yes. And of course, the value risk methodology is focused on this left tail down here, but right now we're just reviewing the normal distribution. So that's our portfolio A. Now, portfolio B is also normally distributed, but this time the mean is only 10%. Well, it's the same, but the standard deviation is 20 instead of 2. So that means the returns are very far spread out from each other. And in fact, for this portfolio A, this is the mean. This is one standard deviation above the mean. This is one below. So the probability in this case of being between minus 10% and plus 30% is 68%. All right, and so what that means is there's a lot more risk with portfolio B than with portfolio A. All right, lots more risk, and you can tell because the standard deviation is so much higher. The returns are more spread out about the mean, although it still has that classical bell-shaped curve to it. Yeah, the returns up here are much closer to the mean on average than down here. So that means portfolio B is much riskier than A. Now, what if I needed to calculate probabilities for very specific situations? For example, portfolio A, with the mean of 10% and standard deviation of 2%, what if I want to know the probability that my returns are less than 12% next year? Okay, so this is the equivalent of saying the probability that X is less than or equal to 0.12. Now, how do I figure that out in Excel? Well, there's a special function built into it that will do this all for us. Now watch how easy this is. It's called norm dist. And what this will do, it asks us for 4 pieces of information. The 12% is the number we're looking for. The B27 is the mean. The B28 is the standard deviation. 1 means this is a less than or equal to probability. So you always put a 1 there. And it comes up with 84.13%. Then if we ask the following question, what is the probability that my returns are less than 14%? I can use the same setup, except now the X becomes 14 instead of 12. And you can see it makes a huge difference. It raises my probability up to 97.72%. And over here, you can see in the graph, maybe I didn't draw that one. All right, I'll do it right here. All right, that's what we're trying to calculate. And so you can see this is actually one standard deviation above the mean, and it goes all the way down. And by the way, these tails go all the way out to plus infinity and minus infinity. Down here with 14%, I'm looking for everything from 14 down. Now here, 14% is actually 2 standard deviations above the mean. So that probability is obviously a lot higher. Now, how about this one though? Greater than 12%. Oh, we haven't seen that one yet. That's this graph over here. Well, the norm function is only designed for less than or equal to probabilities. So we have to make a switch. In order to calculate a greater than or equal to probability, this is the equation you have to use. That's very important right there. In other words, because these two add up to 100% or 1. So we just got through showing that the probability of being under 12% is 84.13. That means that the probability of being above 12% must be, oops, 0.1587. Because the two of these numbers have to add up to 100%. So that means the chances of being above 12% are only 15.87%. And now here's an in-between case. What's the probability that my returns are somewhere between 8 and 12%? Well, there's a couple of things we could do, but the best thing we could do is use our norm dist function in 2 different ways. We're going to calculate the probability that our returns are less than 8% and subtract that from the probability that the mean's below 12%. Whatever's in between is what we're looking for. And so, in other words, what we're saying is that the probability of being between 8 and 12 is equivalent to asking what's the probability of x being below 12% minus 8%. And so we need to use this function twice, which I've shown you down here. This is norm dist below 12%. This is norm dist below 8%, both of which we've already calculated, by the way. And then this is the difference between them. So in between 8 and 12, is actually the middle is 10%, yeah. What we're looking for, approximately 2/3, is the likelihood that our returns are somewhere between 8 and 12%. Oh, let me just quickly save this thing. All right. Now, I do want to point out, and this is very important for value at risk modeling, there's actually an infinite number of different possible normal distributions. Each one has a different value for the mean and standard deviation. Let me just throw this here. There are infinitely many different possible normal distributions, each uniquely characterized by the mean and standard deviation. The most important of these is the standard normal distribution. This has a mean of 0 and a standard deviation of 1. So the formula for VAR requires us to use the standard normal distribution. Okay, it's convenient. That's what it's for. It's really more about convenience than anything else. It's like a benchmark that we can use to judge all the others. So let's say, for example, we're looking for something like this. Suppose I want to know the probability. Oh, by the way, we're going to use the letter Z. I just want to mention this here. By convention, we use Z to represent the standard normal distribution. We use X to represent any other normal distribution. So this number we have here, well, here, I guess, is the so-called Z-score. You may have heard of that before, the Z-score. It represents a specific location under the standard normal curve. So in order to find this probability, we're going to use a different function. We're going to use norm.s.dist. And that function is designed specifically just for the standard normal distribution. So it's kind of convenient. They built that in Excel, so you can use that just for these special cases. Now, with the VAR methodology, we're actually not going to calculate probabilities. We're going to work this in reverse. It's kind of interesting. So let me show you what I mean by that. Suppose, well, let's take a look at this case. Now, remember, with the value at risk methodology, we'll actually be looking at the left tail of this distribution because these are the losses. And imagine the following situation. Suppose this is -1. This is the standard normal distribution. And so what I'm looking at here is the probability that Z is less than or equal to -1. Okay, so I'm going to use norm.s.dist. And I only need two things. The value that I'm looking for, or the Z-score. Oops, I did it again. And the cumulative, just for cumulative, just put true or 1. So it's 0.84. Oh, sorry, I missed it. It's supposed to be -1. 0.15, let's round that to 0.1587. Okay, so we know that the probability is 0.1587. This is the Z-score. Now, suppose we tried to work this backwards Suppose I said something like this. Here you've got a z-score and you're looking for a probability. What if it's the other way around? What if I have a probability and I'm looking for that particular z-score? What would I do then? So what if I'm looking, for example, for the following situation? What is the z-score that corresponds to the lower 10% of the standard normal distribution? Okay, well, let's see, what would that look like? How do I know? Well, for that, there's another special function. We can use the function norm.s.inv, where s equals standard normal and inv equals inverse. So what you would do is you would put equals norm.s.inv, and you would just tell it that 10% is your probability, and say, oh, you mean negative 1.28. Let's round it. Negative 1.28. So you have two different things going on here. First of all, you know that the probability that z is less or equal to negative 1.28 is 10%. But you also know that the z-score corresponding to the left 10% tail of the distribution is negative 1.28. And that z-score is part of our value at risk formula. So that's why I'm harping on this thing right now, because we're going to need that information for our value at risk methodology. And so the tail area will depend on what level of confidence we have or want to have in our results. All right, so for example, if we want to calculate VAR at the 95% level of confidence, we must find the z-score that corresponds to the left 5% tail of the standard normal distribution. So let's do that. So what could it be? Okay, so what we do is we look for norm dot dist s dot in All right, so we put norm dot s dot inv at 0.05, and we can round that 1 to 3 places, 1.645. Which in turn can be interpreted as 1.645 standard deviations below the mean. Okay, so that 1.645 is going to be needed in our value at risk formula, because it represents how far below the mean we have to be before we reach a particular tail of the distribution where our losses are. So all of that was just background so we can understand what's going on here. So over here, I've got a quick and simple example so you can see how this would actually work. Now, this is our VAR formula. Let me just go back to the slides for a second. Actually, no, this can wait. All right. This is what our formula actually looks like. Here we are. We have an investment company that owns a $100 million portfolio. Wow. The daily vol or standard deviation is 2%. We want to calculate 5% VAR at the, or in other words, we're calculating VAR at the 95% level of confidence. Now, the value of the portfolio is $100 million. Now, the Z-score, which we just got through showing, is 1.645, negative actually. The standard deviation is 2%, which we'll express as 0.02. So the VAR actually comes from this formula where V is the value of the portfolio, actually V0. Let me put that in here. It should technically be V0 because that's today's value. Okay, great. Now, here's the Z-score, here's the standard deviation. Look at this formula. This, okay, well, this is the tricky one. This symbol, first of all, this is the Greek letter phi. And it is often used to represent the standard normal distribution. When we attach, you see how there's a -1 exponent? That means we are looking for a Z-score. Okay, and what Z-score are we looking for? Corresponding to a left tail area of C. C is, let's say, 5%. Okay, so that means that this symbol, phi inverse is what it is this number right here. In fact, you know what I'm going to do, just to make it crystal clear. Okay, just so, yeah, so you got V0 for values, Z-score is that phi C thing, and then the standard deviation is the sigma. Okay, so you multiply the three of them together, and that's your 5% VAR. In other words, there's a 5% chance that any given trading day that my losses in the portfolio could be at or above $3,289,707.25, which isn't a whole lot. The reason why it's so low is because the standard deviation is very low. But on the other hand, this is a daily loss. That actually is not too comfortable for a lot of organizations, that you could potentially lose $3 million in a single day. So it's possible that this might be too not conservative enough, let's say, too aggressive for a pension fund or an insurance company, but it might be fine for another type of organization. Anyway, but as far as we're concerned, the risk management group, it's not our job to make these decisions. All we can do is tell the executives what the numbers look like. That's our job. What kind of numbers what are we exposed to? All right, now let's get back to this for a second. I just want to mention a few of the important assumptions of value at risk. You notice that we're assuming normality for the returns to the assets in our portfolio. So that's a reasonable assumption, although it's not perfectly. I mean, yes, returns are close to normal, although maybe not perfectly so. We're assuming that returns are independent from one day to the next, which may not be the best assumption in the world. In other words, if the returns are unusually high one day, we're saying that there's no reason why they should be unusually high or low the next day. Everything will be back to normal, basically. And we know that that doesn't always happen. In other words, sometimes the stock goes through streaks where it has a lot of good days in a row, and sometimes it has bad days in a row. Like right now, Bitcoin is getting clobbered. And so the returns to Bitcoin are clearly not independent from one day to the next. In fact, why don't we take a peek at that for a second? I don't know what happened. I don't really follow Bitcoin, but all of a sudden, completely out of left field, it's crashing to the floor. Look at this thing. 2 weeks ago, it was selling for over $50,000, I think. Yeah, look at that. Whoa, 60,000. And so it would be pretty unrealistic to assume that these returns are independent of each other. It's pretty clear that something's going on. But over short time frames, it's not a horrific assumption, but it is a problem. The statistical properties of returns are assumed to remain the same over time. In other words, the mean and standard deviations don't change, which, over a short enough period of time may not be the worst assumption in the world, but it is somewhat questionable. Now, if these assumptions are true, this is one of the nice features of VAR. The volatilities themselves can be adjusted to any time frame that we need. And in fact, what you're seeing here is referred to as the square root of time rule. And this is awfully, awfully helpful. So in other words, if I had, let's say my volatility over one day is 1%. My volatility for, let's say, a week or 5 trading days would be 1% times not 5, but the square root of 5. And that's approximately equal to, it's like 2.3, I think. 2.236%. 236. Okay, now the reason why this matters is because up to this point, we've been looking at cases where value at risk has been calculated over a single trading day. But the appropriate time horizon for computing value at risk depends on several factors. One of them is the, let's say, the objectives of the financial institution. For example, an insurance company is likely to own very safe assets whose values do not fluctuate very much. In this case, it might be that the appropriate time frame is 1 month. So imagine your insurance company, a large number of your assets are basically either treasury bonds or other safe assets. They're not going to change very much. And so it may be that the VAR can be calculated on a monthly basis, and that's quite sufficient. But on the other hand, for an organization, a financial institution that is trading for profits, the value of its portfolios can change dramatically, so that computing VAR on a daily basis is likely to be necessary. Like, for example, the proprietary trading operation of an investment bank, they need to know something's going wrong in a hurry. A month is not going to do the job. They need to know right away if something is wrong. So for them, VAR would likely be calculated on a daily basis. Now, one of the top, there's an organization, the Bank for International Settlements, in Basel, Switzerland, has published many recommendations for risk management, known as the Basel Accords. Most countries try to follow the Basel Accords. These accords recommend that VAR be calculated on a 10-day basis. Now, I don't remember why they chose 10 days, but they think that for most applications, doing this every 10 days should be quite sufficient. You don't need necessarily to do it every day because it is a very time-consuming process. So that means then that, let's try an example. Suppose that a firm holds a $1 million portfolio with a 20% annual volatility. Well, actually, no, sorry, a 1% daily volatility. And is interested in calculating daily VAR at the 95% level of confidence. The daily VAR would be, and this is exactly what we did before, $1 million times 1.645. By the way, I forgot to mention, when we do these calculations, we do not use the negative sign. It's understood that this refers to losses, so we normally just discard the negative sign. And so 16,450 is the amount we might potentially lose over a given trading day at the 5%, the 95% level of confidence. Okay, now, suppose that this firm decides to follow the Basel Accords and switches to 10-day VAR. How would the results be different? Okay, so here's what would be different. You'd have the same formula. The difference would be felt in this standard deviation. What you would do is multiply sigma by radical 10 to turn it into a 10-day volatility. Okay, so let's see what that would be. 52,000 $19.47 over 10 days instead of 1 day. And so you see how easy this is. And it's because of that square root of time rule. So in other words, what I did was I took the 1 day vol, or the 10-day vol is the 1 day multiplied by radical 10. And that's how I got this number. And that can come in very handy if I need to switch the time frame. Now, the number, if I have daily data, the var that I calculate will automatically be a daily var. If I don't want that, I can then use my square root of time rule to change it to any time horizon that I please. Okay, so that's awfully helpful, but here's the thing, and I'll mention this right now. The square root of time rule is not necessarily completely accurate unless the assumptions are true. For example, independence of returns from 1 day to the next and having the same properties from 1 day to the next. So that's one of the reasons why we make all those strong assumptions, so that we can in fact take advantage of this square root of time rule. All right, so it has the purpose of making strong assumptions with any model is to make things easier for ourselves, but without sacrificing, hopefully, too much realism, because that would be pretty counterproductive. All right, so in my spreadsheet here, I did something similar. I took this example we had a few minutes ago, and I converted it from daily to monthly. Now, of course, that means I'm going to use the square root of time rule, but here's what we have to watch out for. Stocks don't trade every day, do they? They only trade on business days. So we have to make assumptions about how many business days they're in a particular time frame. So here, we're going to assume 22 trading days in a month. Okay, so researchers have determined that that's pretty much the average amount of trading days in a month. So when we use the square root of time rule, what we're going to do take the daily vol, multiply it by square root of 22, becomes monthly vol. And if we want to do this on an annual basis, what we often do is assume 252 trading days in a year. It sounds odd, and it's not the same every year, but that's a pretty good estimate. On average, there should be roughly 252 trading days per year. So we can take our, oh, wait a minute, I screwed it up. This should have been daily right here. So the daily times square root of 252 gives me annual vol, and that means I can calculate the var at that level. All right, so those examples are done. So let me get this out of here. Oh, this will come later.
I just have a question, if you don't mind.
Yes, go ahead.
Yeah, when you do the normal distribution of the returns, how far in the history does one has to go to?
Oh, that's a very good question. Very good question. There doesn't seem to be an answer that everybody can agree on. The thing is, if you go back too far, you're starting to include information that's no longer really relevant. Like if I'm studying Apple stock and I go back 20 years, well, obviously things have changed a lot in 20 years. But if I only go back 3 months, let's face it, 3 months may not be very representative of Apple's history. So there doesn't seem to be an agreed upon number, but realistically, you probably would want to have at least 1 year, maybe even 2 or 3. But at some point, you don't want to go back too far. Like, here's a perfect example of this. Would it make sense to compare stock performances during COVID with before COVID? No. So if you're going to do a study of stocks right now, you probably don't want to go back too much further than 1 year. But if you're just looking at, let's say, the last 10 years, you've got to be careful because you're including both pre-COVID and after COVID stock returns. So it does open up a lot of interesting questions. But the answer is there doesn't seem to be any agreed upon amount that makes sense for all cases. It ultimately will probably depend on how much data you actually have and how far back can you go without moving into a scenario that's very different than the one you're in now. Okay, so it's not really a good answer, but that's the best we can do.
Thank you. Yeah, it makes sense. Thank you.
Yes. And so, yes, there's so many assumptions being made whenever you deal with financial models like this. And in addition to that, how much data are we using and how frequently is it being observed? And so those are all questions that bedevil every economic study out there. But anyway, so here's some ways, just briefly, if the normal distribution assumption is being violated, in what ways are they being violated? In practice, let me draw a picture of this so you can see what we mean. What you're saying is that the returns to stocks, or any other assets for that matter, should look like the normal curve. But in practice, there's a tendency for there to be more extreme returns than you would get with the normal distribution. For example, there should be more area in the tails. There will be more area in the tails, but not quite so much area in the center. Oh, I had it there and I just blew it. All right, let's try that again. All right, that's not the best, but it'll do. The idea here is that you're seeing, no, that's a little better, I guess. What I wanted to illustrate is that the red curve is actual returns. And the black curve is the normal distribution. So there's more large outcomes or more positive outcomes and more negative than you would get with the normal distribution, but there's less in the center. Now, because the value risk methodology is really focused on the left tail down here, this means we have what are called fat tails. That's what they're actually called. And the problem with fat tails is that with fat tails, we are underestimating the likelihood of large losses. Well, that's not good. Now, we're also underestimating the likelihood of large gains too, but since we're analyzing risks, our focus is avoiding big risks. That is a potential problem. It would be like underestimating the value of your house when you buy insurance. Then the house burns down and you're shocked to discover that you can't afford to rebuild it. That's exactly what's happening here. We want to avoid that, but because our assumptions are off a little bit, this is what we're facing with our value risk methodology. The second key way in which the returns are not strictly speaking normal is that there's a tendency for the distribution not to be perfectly symmetrical. But there's a slight imbalance in favor of losses. Let's say, let's try. I mean, it's a little hard to see. Let me exaggerate it a little bit. What I'm trying to get at is that the actual returns, there's an imbalance or a bias, you could call it. In favor of losses. In other words, the returns are not symmetrical about the mean like they would be with a normal distribution. So you're likely to get more losses than you otherwise would if you had truly normal data. Now, so far, I mean, these are not like way off. They're not that bad. I mean, the normal distribution, many models in every discipline assume normality. And so we know that it's not always what's going to happen in practice, but we have to be aware of this when we come up with our value risk results, because again, there's a tendency for us to underestimate our losses because of this. And also the statistical properties of the returns don't necessarily stay constant over time. In particular, volatility can change over time, where we're assuming that it does not. So how would that manifest itself? What you're essentially assuming when you're doing a study like this is that every day the return to your portfolio is randomly chosen from the normal distribution. It's like there's a big lottery going on. And instead of having a ticket, the number on it, it's like the numbers are randomly chosen from the normal distribution. It's like today it's 1%, and tomorrow it's minus 1.7%, and then here it's 0.5%, and down here it's a loss of minus 1.2. This is day 1, day 2, day 3, and day 4. That's what we're assuming. But what if that's not how it works? Let's say, for example, I'll have to exaggerate a little bit so you can see what I'm doing. Suppose we start out with the same nice normal curve. And then the next day, all of a sudden, look what happens. Ooh. And then the next day, it gets really flattened down. And then the next day, it's sort of like this again. So in other words, if this is what's actually happening, that means we're somehow misunderstanding the likelihood of these different rates of return. And that's really, it's kind of awkward, because then we're assuming normality when it may not actually, well, it's not so much the assumption of normality. Even if these are all normal curves, which they are, the means and the standard deviations might be different. So you can see there's all these challenging features that we have. But even like I said, even in spite of all of this, the value risk methodology is still used by everybody 25 years later, which means that at the very least, it's a good starting point for us to help understand how much risk is there in our portfolios. It may be the case that companies, financial institutions, want to supplement this information with other types of measures, but this is a starting point that they can all agree on. This is what it means, and we all understand what the problems are, but we still use it anyway. All right, okay, now, so we've already kind of done an example. Let's do another one. Here's a single asset, and there's our formula. C is the level of, is taken from the level of confidence. The level of confidence is actually 1 minus that. So in other words, if we're using the level of confidence of 95, C is 5%. Or think of it as the left C percentile of the distribution. Now, oh, by the way, I just want to mention there's a couple of cases that we run into very frequently. Let me see if I can find, it's all right. We can look these up in Excel, but the two cases that you tend to see with VAR are 95% and 99%. Those are the two most popular choices. They're not the only ones. So for 95% confidence, that z-score will be negative 1.645. And we've already seen this one. But if we want to be even more confident in our results, we can go all the way up to 99%, which you would do at a very, very conservative organization, like an insurance company. They might use 95%, 99 rather, because they really don't want to run out of money. Imagine what a disaster that would be. So for them, the appropriate z-score is approximately negative 2.33. So you can memorize these if you want to. If you need to calculate these on a regular basis, after a while, you'd have them all memorized anyway. So those are the two most commonly observed levels of confidence for VAR. All right. Now, having said all that, here's an investor who owns $10,000 worth of Hewlett-Packard stock. The volatility on a daily basis is 1.89%, and they did this by looking at historical data, and they calculated the sample standard deviation over that period, and that turned out to be 1.89%. So the daily 5% VAR of the stock, which means 95% confidence, is, now remember here, this is the value of the portfolio. This is my z-score, and this is my volatility. About $310. Not a huge amount, but it's only $10,000. Now, what if we decided to go for a monthly VAR instead of daily? That means we have to adjust the volatility. We have to use the square root of time rule, and keep in mind that we're assuming there's 22 trading days in a month. So we're going to multiply this not by 22, but by the square root of 22. And that's, which is about 4 plus some, let's say. The square root of 22 is approximately 4.69, that's it. So what does that do to our VAR? Oh, I see. So over a month, there's a 5% chance that we might lose $1,458.27 instead of $310 over a single day. So you notice the risk increases not linearly with time, but with the square root of time. Okay. And then I think we've got, oh, annual too. Oh, okay. It's going to be a big number with annual. With annual, we're going to assume 252 trading days. So here, if you notice, I've got, this is my new volatility. The daily, the monthly equals daily times radical 22. Okay. So if I want to amp that up to a year, as we've already seen, times the square root of 252, wow, that's almost $5,000. We could lose almost half the portfolio over the coming year, but you know, it happens. So that I need to know before I decide if I should hang on to the stock or possibly buy an option of some kind, or maybe a futures contract or a forward contract, as the case may be. I can reduce or eliminate my VAR if I hold the right combination of derivatives. But I want to be careful because derivatives can be very expensive. Or I could sell the stock altogether and buy a safer one. That's not such a big deal with stocks. With bonds and other types of assets, selling them could lead to losses. So what we may decide to do is maybe hedge the risk by either buying derivatives or possibly adding to our portfolio other stocks or bonds that are a little bit safer. But here, at least we have a number. And if we want to figure out, suppose we decide that Hewlett Packard is not diversified enough, that we want to add ExxonMobil to our portfolio, we could calculate all these numbers and say, oh, well, here's what would happen to our VAR if we do in fact add ExxonMobil to our portfolio. And then we can decide whether we should do this or not. All right, so you can turn around and say, well, if I also had ExxonMobil in my portfolio, what would that do to my VAR? All right, now sometimes these dollar VARs, as they're calculated, are hard to compare to each other, especially if you have a lot more of one stock in your portfolio than another. So sometimes we replace this with what's called percentage VAR. And all we have to do in those cases is lose the V0. So in other words, you might say, well, here's portfolio A. And here's portfolio B. And so suppose I wanted to calculate the dollar VAR. And this first one is 100 grand. And the second one is only 20 grand. And you might be tempted to say that B is safer than A. But what if portfolio A is 10 times larger than B? And so the portfolio VARs, the percentage VARs are 3% and 8%. Well, then it should be clear that this is actually the safer of the two portfolios. So the percentage VAR is good for comparing our different portfolios or stocks or other assets directly to each other, because then you're not comparing apples with oranges when you compare larger to smaller portfolios. Okay, now the fun begins. Let me see, let me just remind me what's in these. Okay. What about portfolio VAR? Up to this point, every example we did was based on the assumption that we had a single asset in our portfolio, like a single stock. What if instead we have two or more stocks? Then what we're actually doing is calculating what's called portfolio VAR. Now, in order to do this, we need to know the weight or proportion of the total invested in each asset in the portfolio, the volatility of each asset's rate of return, and finally, the correlations among the returns in the portfolio. Now, of course, the correlations tell us represent how closely returns to two stocks track each other. For example, the correlations between oil stocks are quite high because they're all affected by the same variables, of course, especially the price of oil. On the other hand, if we're looking at two very different industries, like the correlations between oil stocks and retail stocks should be much lower because these industries are affected by different economic variables. Now, the correlation measure itself is defined in such a way. Well, first of all, this symbol represents correlation. It is bounded between -1 and +1. You can't get any higher than +1 or below -1. These are perfectly, this happens when two stocks are what we call perfectly positively correlated. They always move in the same direction. And down here, it's the other way around. These are perfectly negatively correlated. Which means they always go in opposite directions. And most of the time, they're somewhere in between. And you can actually draw what's called a scatter plot to help yourself visualize what correlation is all about. So in fact, why don't I do that right now? So let's say you had ExxonMobil and BP. And these are the returns. So you draw a plot which shows the returns of the two stocks at different points in time. And you notice that they're very closely related to each other. We call this a strong positive correlation. Now, the points are not all directly on that line, but they're very close. Let's say the correlation here is 0.9, just to indicate that it's very, very strong. That means that almost invariably when the ExxonMobil's returns go up, so do BP's and vice versa. And of course, it stands to reason because they're both oil companies. When oil prices go up, they benefit. When oil prices go down, they do not benefit. But then let's say you had something like this. Let's say this is General Motors. Now, why did I pick General Motors? Because, you know, it's a manufacturing company. And if oil prices go up, people buy fewer new cars. So their profits are bound to be harmed, and their own expenses in building cars are likely to go up. So I would say that there's a pretty good chance that the correlation between them is very low or possibly negative. And so here you've got what I would call a strong negative correlation. And let's just say, just to make up an example, this is approximately equal to -0.8. Again, it's not perfect. To reach -1, all those points would have to be right on the line. They're not quite there, but they're pretty close. And let's try a third possible combination. What if I have two companies that really aren't truly not related to each other in any sense? Let's say ExxonMobil and Microsoft. Microsoft makes software. They're not overly affected by the price of oil. And so here you might get points scattered all over the place. There's no pattern to them. There's sort of a random jumble of points. And so no correlation. The row is about 0. These stocks have nothing to do with each other, really. Now, I don't know for a fact that that's correct for these two stocks, but it makes sense that they would be the correlation would be very loose because they don't do the same thing. So that's what we're looking for with our portfolio. Now, it turns out that the lower the correlation between two stocks, or any assets for that matter, the less risk there will be in your portfolio. Okay, so in other words, ideally what you want is something like this, because that means that in years when ExxonMobil isn't doing terribly well, General Motors will be doing just fine, and so that will offset your losses to ExxonMobil. Whereas up here, if the oil companies are doing well, you'll have a nice year with your portfolio. But down here, you could really get clobbered. No, we do not want that. All right. So the formula for calculating the volatility or standard deviation of a portfolio with two assets in it, it's kind of complicated looking. And you can see there's our correlation coefficient. And you've got the weights of the two stocks. Let's say this is stocks X and Y. The weight is how much you invested in that stock as a percentage, that is. WY is the weight of stock Y. And what about these other terms? This is the variance of stock X. This must be the variance of stock Y, of course. Now, without the square, this is the standard deviation. And this is for Y. And what are we missing? Anything? The weights, the variances? No, that's it. That's everything. Now, you can see already things are getting very complicated with only two assets in our portfolio. Oh, if we had three or more, let's just say it starts to get really messy. And that's why a lot of research in this area is dedicated towards finding quicker ways of calculating value at risk. All right, so let's see, did I do this in the... This is actually an example. I've already actually done all the calculations for you. What I did was I took these two stocks, I calculated the returns, I calculated the expected return or mean, the variance and the standard deviation. Here's your correlation. I've got the weights, and I have for the portfolio right here, the returns, the variance and the standard deviation. And then here's the value at risk per single year. But what happened here is that this is exactly the same as what you're used to seeing, but the trick was the portfolio volatility. I had to do that. It took a while to get that done. Oh, sorry, what am I doing? That's a standard deviation. Okay, so the challenge when there's two or more assets is right here. The standard deviation is much harder to calculate than it was previously. And I have to go through all these steps, as you can see, to come up with this number. But once it's done, it's exactly the same as what we did before. So once that's in place, now here, the reason why this is yearly VAR is because the data itself is yearly. Okay, just wanted to point that out. That's the data that we have. So that means whatever numbers we get, this is our yearly VAR rather. And in order to convert it, now watch this. Look how easy this is. The monthly VAR, since I started with annual VAR, if I divide that by the square root of 12, it becomes monthly VAR. And then monthly can be converted to daily. by dividing by the square root of 22. In other words, I can go both directions when I use the square root of time rule. I can extend the time horizon and I can shrink it. So that way I can have the yearly var, monthly, and daily as I see fit. So this formula, this is actually this formula right here. And so in the slides, I put in all the numbers. You can see the correlation is negative, which is good. That should reduce the VAR of this portfolio. And I went through all the details and I determined that the volatility of this portfolio is approximately 1.05072%. And then we brought it back here to this, our favorite formula. The 100,000 is the value of the portfolio. This is my Z-score. And this is my daily volatility. So that means for this $100,000 portfolio, every day I might potentially lose, or every 20 trading days, about $1,728. If I want to, then I can extend this to monthly by multiplying by the square root of 22, which brings me up to about $8,100. And then to make this an annual number, I multiply by the daily by the square root of 252, and I come up with approximately $27,000, which sounds like a lot, but remember that's for the full year. If I want, there's another way I can do this too. I just want to briefly mention this. You can actually take and calculate each stock's VAR separately. And then the portfolio VAR actually is very simple. Let me show it to you on the next slide. You see what I've done, and this is another way of doing this. If you calculate each stock's individual VAR separately, you can plug them into this formula and suddenly you have your portfolio VAR. I don't know if that saves a lot of time, but it's possible to do this. If for some reason it seems simpler. Now, there is one advantage of doing it this way, which I want you to see. But I'll tell you what, oh my God, it's already 7:30. I guess we better stop for a few minutes. I'm going to show you one reason why this formula might actually come in more handy than the one we just did. So, but first we'll stop for a bit. We'll have our break. And when we get back, I'll show you why this might be a better approach. And then we'll look at a few extensions of VAR and see other ways in which we can maybe simplify our calculations. All right. So I'll see you in a bit and we'll pick it up from here. All right. So anyway, here's what's happening. We have two stocks. And so StockX is worth $60,000. And we were earlier given the volatility or standard deviation of about 1.6%, 0.016284. So at a 5% level, that means the value at risk of the stock by itself is $1,607.23. Stock Y, worth $40,000, same 95% level of confidence. The volatility is a little smaller at 1.5380%. So the VAR for just stock Y is about $1,012. Now, we're also making an assumption about the correlation between them, which we set up here somewhere was about, yeah, there it is, negative 0.19. So these two stocks do move in opposite directions at least some of the time. So we should get some nice risk reduction by holding these stocks in a portfolio instead of trying to put all of our money in either stock X or Y by itself. So now when we plug in these numbers, now this is the interesting part. We plug in these numbers and the VAR for the portfolio is approximately $1,700. Now, if you notice though, each of stock X and Y had a VAR of over $1,000. So in other words, if you go back and revisit those numbers, you'll see that stock X had a VAR of 1607.23 and stock Y was at 1012, which adds up to 2619.23. So how come the VAR of the entire portfolio was only $1,700? Well, that's where this negative correlation comes in handy. The risk of the entire portfolio was reduced because of the fact that these two stocks tend to move in opposite directions. So in other words, when stock X is having a rough year, stock Y can compensate for that with a good year and vice versa. So the risk of the entire portfolio is smaller than it would be if we simply held each one separately and then added these up. So what happens here is that we'll assume or we'll define what we will call undiversified value at risk, which is what the portfolio VAR would be if the correlation between the two stocks was exactly equal to 1. In other words, they're perfectly positively correlated. So based on this formula, if we replace that correlation with a 1, it turns out that the portfolio VAR will simply be the sum of the two individual VARs. In other words, if these two stocks had a correlation of 1 between them, the value at risk would have been about $2,600. Instead, it was about $1,728.43. So this is referred to sometimes as diversified VAR because it comes from a portfolio with two diversified assets, as opposed to undiversified VAR, which is as high as it can go because we have a correlation of 1. So the difference between the two is referred to as the benefits of diversification. In other words, you take the highest possible VAR, which is undiversified, subtract your actual VAR, and whatever's left over represents how much risk you've reduced by holding a portfolio of stocks rather than just holding an individual stock. So here, that adds up to about $890. So in other words, you can tell how much risk you've reduced just by calculating the diversified VAR and the undiversified VAR. And so in order to do this though, like I said before, you need to use this formula right here, this one. Otherwise, it's not realistically, I mean, you could probably do it with the other formula, but this is the one that makes it easier to do this. All right, now, what happens when we have complicated assets in our portfolio? What happens if we start adding options, for example, or other types of securities? Then the calculation of VAR can get extremely complicated. So there are shortcuts, though, that we can lean on. For example, you remember from last week, we talked about the Greeks. The delta is the Greek that tells us how sensitive an options price is to changes in the value of the underlying asset. So the call delta is the change in the call price with respect to the stock price or whatever the asset happens to be. And the delta for the put is the change in the put price given a particular change in the stock price. So what we're going to do here is see how you could actually calculate the VAR of a portfolio that contains options by adjusting the formula to incorporate these deltas. Now you might think, well, how's that possible? Well, it is possible, very possible. So let's see, what do we have here? We've got 100 IBM calls with a delta of 0.6. This IBM stock is selling for $50 a share. The volatility is 30% per year. We also have 50 GE call options, each with a delta of 0.72. The GE stock is selling for $80 a share, and the volatility is 20%. And furthermore, the correlation between the returns is 0.5. What we'd like to do is calculate the VAR of a portfolio that consists of these two options. Well, what we can do is use the approach we just followed. For example, the first one, the 100 call options, the stock is worth $50. So S is 50. And we have 100 call options. Each with a delta of 0.6. So what that means is that the sensitivity of the stock, of this call, to changes in the stock price is the same as holding 100 times delta, or 100 times 0.60, or 60 shares of the stock. Okay, so this is the logic that we're about to follow. In other words, you know what delta means. And also, by the way, I want to remind you that the delta of a share of stock is just 1. As a stock. A stock's delta is 1. So what we're basically doing here, in order to make this a little simpler, we're saying, listen, based on that delta of 0.6, 100 options with a delta of 0.6 is equivalent to holding 60 shares of the stock as far as the sensitivity to the price of the stock. And because the stock is selling for $50, we can pretend or treat this portfolio as if it contained $3,000 worth of the stock. In other words, 60 shares at $50 each. And we can use that information to come up with the VAR of just those 100 options. Okay, so we're going to do it in the following way. That's this one, by the way. So we have the equivalent of $3,000. Okay, so this is, think of this as, again, 60 shares, or think of it in 100 calls equals 60 shares as far as risk goes, which in turn is worth $3,000. This is the Z-score, of course, that goes with 5% VAR. This is the volatility of the stock that the options are written on. And so for that portfolio, we have a VAR of $93.27. For the second set of options, let me just go back and read the details here. For the options on GE stock, we have 50 options with a delta of 0.72 each, and the GE stock is selling for $80 a share. Okay. So based on the logic we had before, 50 shares, 50 calls with a delta of 0.72 is the equivalent, as far as the risk goes, of 50 times 0.72, which is 36 shares of stock. In other words, 50 calls have the same delta as 36 shares of stock. So as far as the risk goes, we may as well treat it as 36 shares of stock. And by doing so, we can use the same formula. And remember, the stock is currently selling for $80 a share. So multiply that out. And that gives me a value of $28.80. So when it comes time to calculating the VAR of just these 50 calls, I can treat this as if it were a portfolio of $2,880 worth of this stock. And then I can use the volatility of the stock. Oh, and by the way, one more thing, I just want to mention it. It says here in the problem that the annual volatility for GE is 20%. Where did this number come from? I just want to remind you that this would therefore be 20 over 252, square root of 252, approximately 1.26% per day. And similarly, we were told that for the first set of options, the 100 options on IBM, the annual volatility was 30%. And so this 0.0189 is actually 30% divided by square root of 252 because of the square root of time rule. And so when we're done, the GE options have a daily VAR of 59.69. Now, the last thing that remains to be determined is the correlation. And so here, because we're treating this as a portfolio of stocks, we can think of the correlation as as being between IBM stock and GE stock. Now, this is hugely important because it's easy to calculate the correlation between two stocks. These stocks trade every day. There's a lot of data available for their prices. Not so with options. Options don't trade very often at all. And so getting a correlation measure between IBM and GE options would be extremely difficult, whereas getting the correlation between IBM and GE stock is infinitely simpler just because we have so much data. So therefore, using the method we had earlier, if we assume that the correlation is 0.5 between IBM stock, not the options, IBM stock and GE stock, and it's equal to 1/2, then we can plug that into our formula, along with the two VARs that we just calculated. And all of a sudden, we figured out without too much difficulty, the VAR of 100 calls on IBM and 50 calls on GE is equal to 133.53. That's daily, by the way. Now, but the whole idea here is that we didn't actually calculate this based on the calls themselves. By using the concept of delta, we were able to rearrange the formula and use it and apply it, that is, to the actual stocks because of the equivalence between the risk of the options and a fixed number of stocks. So therefore, you can see that this is one of the many ways in which we can simplify value at risk calculations. So it's, and without that, I mean, like I said before, it would be very difficult to calculate the value at risk for an option under normal conditions because they first of all, they have very short maturities typically, and secondly, they just don't trade very often. So coming up with good data would be a big challenge. So that's why this is such a helpful approach. All right, anyway, one thing now, here's there are problems with value at risk. And there's this sort of extension to value at risk that we see sometimes called expected shortfall. What exactly is that all about? All right, well, here's one of the major problems with value at risk. I mean, besides all the assumptions, one of the drawbacks to value at risk is that it only shows the cutoff point between the lower, let's say 5% tail, and the rest, or actually I could just replace that with C. It could be any value we want, and the rest of the distribution of portfolio returns. It does not tell us what kinds of losses can occur in the left tail. So in other words, it's just showing us the cutoff point between the worst outcomes and the best. So it's basically saying, all right, well, if you want to know how bad things can get, we can reach this point or worse. So let's say that we have something like this. We have $1 million portfolio, and let's say the value at risk is here. This loss of $100,000 is my VAR. And this now represents, let's say, the bottom 5% of my distribution. The VAR doesn't tell me, though, what could happen. Well, let's say I end up down here somewhere, or down here. The VAR is just telling me the threshold between the lower 5% of the distribution and the upper 95%. So in order to supplement this information, researchers invented this measure called expected shortfall, which, by the way, it also has other statistical properties that the VAR doesn't have. But the main purpose of expected shortfall is to give us a sense of what could happen in this tail. And so it's a very simple idea. What they're basically doing is saying, well, listen, why don't we go in there and see what could happen in that left tail? And so, for example, let's keep the same situation going. This is the left 5% tail. But what if we did this again with the left 4% tail, and the left 3%, and the left 2%? And this one is, let's say, 800,000. And this one is 700,000. And this is 600,000. With the expected shortfall, what we're seeing is the average of the values at risk in the left tail. So let's say that this is my VAR. If I average all these out, my expected shortfall might be, for example, 160,000, which means that, yes, the cutoff point with the left 5% tail is 100,000. But if I do end up in that left tail, on average, I can expect to lose about 160,000. Those are all the other losses that I've kind of overlooked by just calculating VAR by itself. So the expected shortfall is a good way to supplement our VAR measure with more detailed information about what could happen in this left tail. And it's not hard to calculate. I mean, you're essentially just calculating VAR with different levels of confidence and averaging them out. Now, how many of these you can do depends on how much time you have, because remember, this is still a very time-consuming process. But let's just imagine the following scenario. You've calculated all these different VARs, okay, like we've done all this whole time. And here's the left tail, and I've lost 20,723.21. I do it again for 4 and 3 and 2 and 1%, and I average these out. What do I come up with? Well, it turns out, I'm reading it from the next slide, the average is 25,234.09. And I think you'll agree this is much more useful than just the VAR by itself. So if I hit the left 5% tail, my VAR is about 20,723, but if I land in that tail, my average loss should be in the neighborhood of 25,234.09. Now, I did prepare a separate spreadsheet for this, just so you can see how these kinds of numbers are calculated. But it's exactly like what I just said. I took the same information we just had, and what I did was I recalculated the VARs. Actually, this is a slightly different example. This goes back to the one we had a few minutes ago. This one, no, not this one. The first portfolio VAR that we did. Yeah, this one. Okay, about $1,728. So all you would have to do is say, well, let's recalculate this at these different tail areas. And so what will be different in the formula each time is the Z-score. All right, that's the only thing that has to change. And there it is next to it. You see this column, the Z-scores keep increasing as we move further onto the left tail. The value of the portfolio doesn't change. The standard deviation doesn't change. All that I'm changing is the Z-score. Come up with my different VARs. I average them out, and now I've got my expected shortfall, which is about $2,104.48 compared to the VAR, which is about $1,728. And you might recall this we did earlier, the diversified versus the undiversified VAR. That's all being done right here. Yeah, basically this is what we did in the slides. All right, well, anyway, so this was just sort of the tip of the iceberg about value at risk. We didn't really have that much time to do any hedging, but the calculations are very complicated, as you can see, but this is a very useful framework because it means that no matter what assets are in our portfolio, we can come up with a single number which represents the risk of the entire portfolio. And that makes things a lot simpler than in the past when we would have had risk measures that couldn't be directly compared to each other. Like, for example, the beta of a stock, the duration of a bond, and that type of thing. You could not combine them in any meaningful way. Here you can do exactly that. So you've got just a single risk measure that applies to all assets in the economy. And so in spite of all of its unrealistic assumptions, it's a very popular tool in the risk management industry. And once they have this information, they can sit down and say, well, you know, should we sell some of these stocks? Maybe we should buy some derivatives. If we do, what happens to our VAR? So this is all a very important area where derivatives are heavily used. And so the point of all this is to show how the risk of our portfolio changes when we add options or futures to it. so that we can figure out exactly how much risk we're reducing. Otherwise, we're kind of guessing. All right, so I think that's it for this topic. I mean, we obviously could have spent a whole semester with this stuff. And in fact, we used to do exactly that. We used to offer a 2-semester sequence in not value risk, but a risk management in general. And it was quite interesting, but for some reason, the interest in it kind of fell off. You know, the thing is, in the 90s, when all of these results were being developed, there were also several financial crises that broke out, and which made it clear to all the financial institutions that they need to really beef up their risk management measurement and modeling and all the rest. And so this whole field of risk management came into being. And at first, everybody wanted to get involved with it, but I guess after a while, they kind of reached a saturation point. And so now, you know, for whatever reason, nobody signed up for the risk management class, so we had to give it up. But the derivatives themselves are just a small part of this field of risk management. So anyway, so if there's no last minute questions, I guess we're done. Now, I did say that I'm still working on your assignments. I'll send them back to you probably tomorrow with corrections if there are any, and I'll post the grades in the NYU's grade book. I have to go back and remind myself how that works, but I should have all that stuff ready within the next couple of days. From what I saw, people are doing very well with their assignments, and that's good because the grade is entirely based on the assignments. And so if you can handle those Excel spreadsheets, then you really have a good handle on this stuff. So anyway, yeah, I guess we're done. And it's kind of sad when this class ends because it's so exciting and there's so much more that we could do. But who knows, down the road, maybe we'll have a more advanced derivatives class, and then we can really go to town. But in the meantime, I hope that you got a lot out of this class, that you learned a lot, and that you'll be able to apply it to other areas of study, in particular your concentration, and who knows, maybe even on your jobs. So anyway, so if nobody has anything else to add, I guess I'll wish you a good night. And who knows, maybe I'll see you again in a later class.
Thank you so much, Professor.
Okay, you're welcome.
Thank you, Professor.
All right, you're welcome.
Thanks, Professor.
Okay, all right, bye.